Hi everyone, I'm Geir Arne Gjelle, and I'll be teaching this Introduction to NumPy tutorial. Day to day, I work with a website called RealPython, so I'll throw in a few RealPython links here and there. So RealPython is a site where you can go and essentially find tutorials on Python. So we have some stuff on NumPy as well. I've been working with Python now for about 10 years in different scientific applications, doing a lot of work using NumPy in the background, which is kind of what I will be talking about today. But just, before we start, let's see how to phrase this properly to get the answer. Who of you have not used NumPy, at least consciously, before? So show of hands. Okay, so some of you, but most of you have, in some respect, used NumPy. What I'm going to do today is kind of talk about what is NumPy, where does it kind of sit in the whole ecosystem of scientific Python packages. Then we'll talk about NumPy arrays, which is kind of what NumPy is all about. It provides a data type called an array. We'll talk a little bit about how to create these arrays in different kind of ways, how we can index into them and kind of work with them. Then we'll look at how we can generate random numbers in NumPy. So NumPy comes with a very powerful random number generation mechanic that may be useful in some projects. We'll talk about one of the real superpowers of NumPy and what kind of makes it useful for scientific application and what really makes Python useful for scientific applications, which is called vectorized operations. We'll see a little bit about how we can do linear algebra with NumPy. And then we'll end with talking about something called broadcasting, which is another really powerful mechanic. The material for the tutorial is on my GitHub page, so the link is up there. I also shared a link on Telegram. So those of you who are on the Telegram EuroSciPy group, you should be able to find it there on the beginner tutorials. What I plan to do here is essentially show a little bit up on the screen, and then inside of the GitHub repo there are exercises that you can kind of attempt on your own. I'll be using the notebook, as you can see here. You can follow along really in any kind of Python setup as long as you have NumPy installed. So follow along in the notebook yourself, or just an interactive Python shell, or whatever you makes sense to you. If you're used to kind of working in, say, VS Code, you can probably do that as well. So, okay, so let's kind of just start with the basics. So NumPy is not a part of Python itself. It's a third-party library. But if you have installed a distribution like Anaconda, then you already have NumPy available. If any of you run import NumPy and you get some error message saying that you don't have this module installed, then you need to install NumPy, which you can do if you're on a Conda platform with Conda install NumPy. If you're not, then you can use pip install NumPy, essentially. So if anyone are not able to run this, definitely let me know and we can figure it out. But yeah. We'll import NumPy as NP is the typical convention. You can definitely just import NumPy, but essentially everyone uses the NP shorthand, so we'll use the same. And let's just have a look at the NumPy array. So the basic kind of workhorse for creating a NumPy array is a function called np.array. And this one you can send in kind of anything in Python that's a sequence initerable. So if I just do something like this, I send in the list 1, 2, 3. What's returned is just an array 1, 2, 3. So it's kind of the exact same elements, except that it's wrapped into this NumPy thing. And while it doesn't look like much on screen like this, it is actually a lot of stuff happening underneath that gives us the power that we want. And to give you a little bit of background of why this is important, and we'll kind of see this now in the next example, is that Python has a very flexible list structure. So if you've been using lists in Python, you may know that you can kind of mix in anything you want into a list. So if I create a list in Python, say something like this, I'm allowed to mix all kinds of elements into a Python list, which creates a lot of flexibility, although in practice, you very rarely work with data structures which are a little bit of numbers, a little bit of text, a little bit of whatever. So while this gives us a lot of flexibility, it also means that Python ends up being very slow working with these lists, because for every element it needs to check, is this a number, is it a string, and those kind of things. So NumPy takes away a little bit of our flexibility here. As we can see, if we now try to wrap the same thing into a NumPy array. So if I do this in NumPy, you can see that I'm getting back something similar, but it now looks a little bit stranger there. And if we look closely at this, we can see that it's wrapped, or it's actually converted every element into a string. You can see there are quotes around each of the elements. And then in this case, NumPy also mentioned that there's a D type, which is this weird collection of characters there. But essentially, it tells us that this is Unicode, 32-bit Unicode. So what has happened here is that NumPy is kind of enforcing that one array needs to have the same data type for each element. So you can't mix and throw in strings and numbers and booleans and all kind of things into a NumPy array. It needs to be the exact same type. So in practice, NumPy arrays will typically be integers, floats, or booleans, I guess, are the most common ones. And this immediately means that things can be a lot faster, because you know exactly how much space each element takes up in memory. When we're working with NumPy arrays, we rarely need to care about this, but that's kind of the magic sauce that NumPy uses under the hood. And it's kind of the one limitation that you'll feel if you compare to lists. The data type, as you can see, it's kind of enforcing, in this case, things to be strings. What you may run into more commonly is something that may or may not be important. So if we do something like this, now I have a list of numbers. So I get the NumPy array of numbers. But in the first case, let's see, the number 2 up there, each of the numbers were integers, right? 1, 2, 3. And what NumPy returned is an array that contains integers. In number 5, the last one there, you can see I entered the integers 1 and 2, and then I entered a float 3.14. And in this case, it's kind of subtle in the output, but the 1 was turned into 1 dot, which indicates that it's a float. So now all 3 numbers are floats. So you can kind of enforce this or be more explicit about it. So I could also do something like NumPy array. Now I just do 1, 2, 3, but I say that I want the data type to be float in this case. And now you can see that, again, it kind of has the telltale dot at the end there. So if you're working with data that you know this should be treated as integers, this should be treated as float numbers, it's good to be explicit about it. And it's also possible to be even more explicit and say things like float 32 or float 64 or things like this. So these are data types that indicate that it's a floating point number, but with so and so much precision. So a 32-bit floating point number has less precision than a 64-bit, which is the most common one, which may be important if you're working with really small numbers or precise numbers. But they also take up less memory, which may be important if you have a lot of numbers and things like this. Okay. Another kind of superpower that NumPy arrays have over Python lists is that they are better at handling higher dimensions. So first of all, let's just have a look at let's see, yeah. So if I do one of these NumPy arrays, and then I ask it for what's your type. So type is a Python function that you can use to just investigate what is the type of this particular data structure. And you can see here that this is a numpy.nd array. And all NumPy arrays are named nd arrays, where the d means dimension, and the n essentially just then mean it's an n-dimensional array, which kind of hints that NumPy arrays can be of any dimension. So you can work with them as one-dimensional arrays, which is often thought of as vectors, two-dimensional arrays like matrices, or three-dimensional arrays, 12-dimensional arrays if you want to, and so on. These are sometimes also called tensors, but it's kind of the idea. You can make things as many dimensions as you need. In practice, I guess two dimension is, at least in data science, it's typically what you end up with and so on. But how do we create these arrays of higher dimensions? So if you just give NumPy a nested list, that's kind of one way to just start this. So you can see if I do something like this, now I have a list of lists. So the first nested list is 1, 2, and the second one is 3, 4. And the printout there kind of shows us that this gives us like a matrix of numbers. It's a 2 by 2 matrix, or it's a two-dimensional array, you can think of it. And we could even run off and do this as a, yeah. I'll do the third dimension, but then I guess we'll stop. Let's see. So typically, if you're working with higher dimensional things, and really, in general, I guess it's quite rare that you end up typing in your arrays manually like this. You'll get your data from somewhere else. But let's see if we're able to do this. So this is now a three-dimensional array. Of course, once we get to 3 dimensions higher, it's harder to represent these dimensions. So you can see it's kind of more represented as a list or something like that of two-dimensional arrays. But we can actually check now that if let me copy this. I copy this array and just ask for its ndim. So that's the number of dimensions in my array. Or we could also ask for something called the shape, which is the number of elements in each dimension. So in this case, it tells me that this array is a 2 by 2 by 2 array. Okay, is this working out okay for you as well so far? No big problems?
Why is there a space between the two first and the second?
You mean up here? So yeah, so the question was, why is there a space in the printout between the two 2 by 2 arrays? And it's just an indication that these are not, it's kind of to help you read it, essentially. So to show that there's 3 dimensions up there. So it's mainly just to try to help people to understand what's being printed out. Okay. And yeah, do feel free to stop me at any time and ask questions, by the way. So far I've kind of just shown, okay, we can create arrays by doing np array. And this we can do on, as I mentioned, any Python object that you can kind of iterate over that gives you some values. So just to show you one example of that. In Python, there's something called a range. We'll see more about ranges soon. And a range is just a list of numbers, essentially. So if I ask this range, if I just create a Python list from it, you can see that the range of the 6 first integers is 0, 1, 2, 3, 4, 5, for instance. We could immediately create a NumPy array from the same range like this, and we get the same thing, only wrapped in an array. So anything that kind of you can iterate over like this. However, NumPy has a lot of built-in special functions to create arrays. So to show you a few of those at least, there's one called np.zeros, and this just creates an array filled with zeros. And then you can just give it a size. So if I want to have a 2 by 3 array of zeros, I can just do something like this. This may not immediately seem useful, but one thing you can do with this is kind of just prepare your array and then go in and change some values in it later. You can also control the data type in these kind of special functions. So we could do something like, let's do this, like this, where we say that, okay, the D type should be int8, which means 8-bit integer, which is a data type that can keep just the numbers from 0 to 255. There's also one where you can do, let's do this then. You can get just an array filled with ones. And with the 1, you can also go in and just multiply by any number, which we'll see later, to create other numbers. Then, yeah, we briefly talked about range above. And NumPy also supports a range directly in NumPy. So I could do something like this to just do the same kind of range directly. And this one is somewhat powerful in that you can also do several parameters. So if I do something like this, what I'm saying is that I want the range of numbers starting at 1, ending at 2, and the step between each should be 0.1. So that kind of then gives me this array. Just a quick note that it will not include the endpoint in your range. So you can see that 2.0 is not included there.
What is the difference between using range and range?
Yeah, so range is a built-in into Python, and arange is built-in into NumPy, essentially. So your range will be just a Python object, and then you need to wrap it in something like the NumPy array, like we did up here, to get the NumPy out of it. With arange, you immediately get the NumPy thing. One of the difference is that the built-in Python range only supports integers. So if you need to do something with floating point ranges, then you'd need to use the NumPy one. Here. And let's see, there were a few others I wanted to just quickly show you. Yeah, so one that's kind of related to range is called linspace. And you use it to kind of create the same type of equally spaced ranges. But in this one, instead of kind of giving the steps, you just tell it how many points you actually want to have in there. So to create at least a similar one, I'll do something like this. Here I'm saying that I want a range between 1 and 2, and I want 11 points in my range. And partly to confuse us, I guess, but I think it makes sense. Linspace includes the endpoint by default. So you can see that in this case we get the 2. And that's also why I said I wanted 11 points and not 10, which may have been the intuitive thing to put in there. There's a few special functions that are more related to linear algebra, but I'll just show them now. So one is just I. In this case, it's more about the sound of it than the meaning of the word I. It's the identity matrix. So this, you can see it's just 1 on the diagonal and zeros all around. And there's also one where you can just define the diagonal. So we'll talk more about matrices later, but if I do something like this, you can see that this gives me In this case, a 3 by 3 matrix with 1, 2, and 3 on the diagonal, zeros otherwise. Okay, yes, yeah. Right. So I think that both the identity matrix and diagonal one kind of makes sense in 2 dimensions, so it's kind of related to 2D matrices. I don't think you can use them in higher dimensions immediately. Yeah, well, this should immediately go there. We can quickly just check. Yeah, I think it's not immediately. By the way, this is, if you haven't seen it before, in Jupyter or IPython, you can use this to get help on stuff. Yeah, it wasn't very explicit, but I think this is essentially always returning 2D arrays. And yeah, the diagonal in higher dimensions kind of gets a little bit harder to think about. Okay. I'm just going to show you a few more index stuff, and then I'll let you play a little bit with an exercise yourself. So let's just define one of these things as a matrix with the name. So I'll just do something like this for an example. So I'm just defining a 3 by 3 matrix. And I messed up, yeah, the nesting. So here I have a matrix, I called it A, so I can refer to it. And if you've been using Python lists, you know that you can index into them, which means that you can kind of pull out individual elements. And we can do the same thing with NumPy arrays. Now, they may be higher dimensional, so we'll see how we can use indexing in higher dimensions as well. But the first thing you can see here is that I just ask for the element at index number 1, or index 1. First of all, I use the square brackets in this case, and I say square bracket 1. Now, Python in general and NumPy as well counts from 0, so this ends up being the second row, I guess, in our array. So you can recognize that it gives me now a one-dimensional array. So I'm essentially taking the dimension down from 2 dimensions and down to 1 dimension, and this 1 is now the second row there. So index 0, index 1. So that's kind of what it gives back to me. I can also, with use several indices, just separated by comma, 1 per dimension, really. And in this case, for each index I give it, it kind of takes it down 1 dimension. So now I'm asking for index 1, comma 2, which is, again, the second row, and then the 2 there represents the third column. So again, counting from 0. So it's the answer is 1, and that's this. It's the one that's up there. That's kind of returned. There's also something called slicing when we do indexing, and this gives us a chance to kind of pull out sub-arrays. And to show you, I can do something like 1:3, and when I throw a colon in there, it's kind of like a range again. So it means that give me all the elements that starts at index 1 and ends before index 3. So that means 1 and 2 in this case. So you can see that this gives us the last 2 rows. Or I could also then do this in more dimensions. So we could do something like this to kind of now pull out the two first columns. There's also a shorthand where you don't need to write out the last column or the first one. So I could do the exact same thing just by skipping the numbers like this. So you can see when it says 1 colon, and then it means to the end. Or when it says colon 2, it means from the beginning until 2. And that means that the way to get, let's see, the way to get a hold of columns. So we saw, we could easily get a row just by indexing with one variable, but I can also go in and just say that I want all the rows by using a colon from the start to the end, and say that I just want the second column, for instance. And then one final little trick we can do when we are indexing is that we can actually, so far we've seen that we're using indexing to kind of either pull down dimensions to less dimensions or just get a subarray, but we can also actually increase the dimensions. So if I have my, let's see, A, I could do now something like say that I want to throw in a new axis in the middle there. And it's not directly easy to see from this, but we can see we have this, the blank line in between, and you can see there are 3 opening brackets there. So now this is actually became 3-dimensional. So I'm just saying that, okay, I want to keep the first dimension, I want to keep the last dimension, but I want to throw a new axis in the middle. So we'll see a little bit more how these new axis things work later, but just to show you that from my 3x3A matrix, this thing now became 3x1x3. So it kind of has one element, so it kind of became a slice in 3 dimensions, more or less. As a last example here, I'll also just show you there's a function called reshape, which you can use to also just have the same elements, but just change the shape of it. So for instance, in this case, I reshape A to be a 9 vector, essentially. So flatten the whole thing. Okay. Any questions so far? You kind of just seen a lot of, okay, now we're creating arrays. We haven't really seen too much about what we're going to do with them. But yeah, just to play around a little bit with this yourselves. If you look at the GitHub repo that you hopefully have downloaded, or you can also just click into it. If you click on exercises or look into the exercises folder, there are a couple of exercises just to play a little bit with this. So for now, let's just do 5 minutes where you can have a look at this. And then if you want to check your solutions, there are suggested solutions also in the solutions folder. Yes, so let's see. I can probably just do this. Is it readable up there? Okay, I think we'll move on. Any questions to anything in the exercises or what you've seen so far? No. If you need to, there are solutions or suggested solutions also in the repo there. Random numbers are surprisingly useful when we're going to do different kind of work. And NumPy has its own module or submodule dealing with random numbers. So I just want to show you a few examples of this. And it's we're not going to dive deep into all the possibilities there, but I just want to show you kind of the gist of how it works. And one kind of important disclaimer when working with random numbers is that there are never, say, completely random numbers. And it's usually not a big deal for most applications. Your numbers are pseudo-random, as they're called, because they're created by some deterministic process. But in some applications, typically around security, you want to have numbers that are harder to predict than, so that's not sort of like an attack vector into your security. So NumPy random numbers are not cryptographically secure, so to speak. So don't use them to generate your passwords, essentially. But they're more than good enough to do to work with in different scientific settings. So let's see. Okay. So NumPy and random numbers is kind of located inside of np.random, which is a full module about dealing with random numbers. And I think, let's see, it kind of comes with, what I kind of just wanted to show you briefly here, it comes with a lot of different probability distributions so that you can draw random numbers from different distributions. So you can kind of say, I want to draw normally distributed random numbers. I want to draw uniform random numbers. I want to Poisson distributed random numbers, and so on. So most of the well-known distributions are available within the module. We'll see a few examples of this, but there are many others that we won't look at. It also comes with something that we're definitely not going to run into much, different kind of generators. So unless you kind of know that you need to be extra careful or looking for special properties, just run with the default one. But there are different random number generators that you can use. And then this is mostly what you need to know about to work with NumPy random numbers. Call this function. The RNG there means random number generator, and it gives back an object which can generate random numbers for you. So we'll see exactly what this means now. So it tells us to call default RNG. And you can see if I just call this, I get back a generator. So this is a random number generator. It says PCG64, which is kind of the method it will use to generate random numbers. But typically what we'll do with this is that we'll just assign it to a variable, often just named RNG. And then you can use this RNG object to generate your random numbers. So for the very basic example, I can now just do RNG.random. And what you should observe if you run this code yourself is that you don't get the same answer as I do. It's random. But what I briefly mentioned is that it's really pseudo-random in the sense that it has been constructed through some kind of deterministic process on our computers. And we can kind of control this process. And sometimes that is useful to kind of have a list of numbers that are random, but they're still reproducible. And the way to do this is that you're talking about, or you're using something called a seed that you use to initialize your random number generator, and then that's kind of number that it starts from, and then it does this deterministic process on top of this number to generate the next one. So we can create a new random number generator. So I'll call default RNG one more time. And now I'll introduce a seed, which can really be just any number. So I'm just using 2023 for this one. And if I now do rng.random, I get a new random number. And it doesn't look like this one is any more special than the one above. But if you now run the exact same code as I, you should get the same random number. Now I can notice that if I do RNG random one more time, I get a new random number again. So the seed is kind of just initializing the first time I call it, and then each time I call it, it will still be in this reproducible order, but we do get random numbers from it. But I can show you now if I go up and just copy my RNG, and then I'll run rng.random. You can see that since I had the same seed, I get the same random number one more time. So this allows us to work with random stuff, but in a reproducible manner. Yeah, this random thing, that's usually not what you want to use when you're dealing with random numbers. It just gives you a uniformly distributed random number between 0 and 1, which may or may not be what you're looking for. So there are other distributions or functions or methods that you can use. So one is just this uniform, which you can see here. It takes in parameters low and high, so that you can control what you want to do with it. So we could here say that I want numbers between 0 and 10, for instance. And then I want this to be a 4x2 array. So something like this will then give you all kind of different sizes. Or maybe I want some normal distributed numbers, and I want 20 of them. So this gives me a one-dimensional vector of 20 normally distributed numbers. And the different distributions come with different parameters. So for instance, the normally distributed numbers, they're kind of focused around some kind of peak. And if you look at these, you can see that they seem to be centered around 0. There are some slightly smaller than 0, some slightly higher than 0, but they're more or less centered around 0. So when you're talking about normal distribution, you can also then say, I want this to be centered somewhere else. So I could go in here and say that I want to have numbers that are centered around 10 instead. And I could also say something about how big the spread should be. So in this case, you can see that my numbers kind of range not too far away from 10, plus minus 1, 2-ish. So I can do something right, range normal, 10 with the spread of 5. And you can see that now I get numbers further away from 10, but they're still more or less centered around 10. Okay, any questions about random numbers? So let's just do a quick look at the example or exercises. So this is essentially just playing a little bit with the seeds and random number generators just to make sure you get them. So it's kind of similar to what we have been doing so far. And if you want to try something a bit different, the last exercise here, asks you to just create an array of square numbers and sample stuff from that one. So we'll have 5 minutes with these exercises.
I don't get how this choice works.
Let's see, yeah, so that was just a question about how choice works. Yeah, we'll do the quick example of that in a minute or so. Okay, I guess we'll move on slightly. So yeah, the first two exercises was kind of redoing a little bit what we've already seen. But for this third one, just want to show you the rng.choice function. And I think we're also just gonna use the opportunity to kind of show you what's coming next, so to speak. So we've seen that we could do something like this n range, a range, to just get an array of numbers. And one of the powerful things in NumPy is that we can do what's called vectorized operations on these things. And it means that we can work on a whole vector or a whole, really a whole array, as if it's just a number, more or less. So you can see now if I take this range of numbers and just say star star 2, it means to the second power, I get squares immediately. So under the hood, NumPy is kind of doing the looping for us, and we're going to see much more examples of this shortly. The exercise tells us to create this this array squares. You could also just create this array manually or with loops as in regular Python and so on. And then we're going to use a pseudo-random number generator to just sample numbers from this array. So first I need my random number generator. Random default RNG. And once I have that one, there is a function called, or method I guess, called choice that generates a random sample from a given array. So what I can do with this is that I give it an array, and then I tell it how many elements I want to sample, and also whether I want to replace or not the elements that I sample. There's also a couple of other options, like we could give different probabilities to each element and so on. But in this case, it asks us for 20 elements. And we guess we don't need to specify this since it's default, but just to be explicit, we want to replace in this case. And you can see that I'm now getting, let's see, I can remove this. I'm now getting just these squares, but some random sample of them. Did that more or less answer things? Or no?
So it's
yeah, I can.
So it's a random choice of things which are contained on that array. Is that?
Yes, exactly.
Okay.
So it just takes, starting from the pool of squares that we have, it just one at a time samples them. And since we have replace equals true, it kind of, okay, I found 64. I'll put it back in, and then I take another one, put it back in, take another one. If we had done something like this, let's see, this should not work, I guess. If I do replace false, because I can't take 20 numbers from a bag of 10. But if I do just 5 of them, we can see that now I take 64, and I don't put it back in, so I can't draw 64 anymore. So if you do replace false, you'll always get different elements. Any other questions? Okay, then let's dig into these vectorized operations. And I'll also show you an example of the difference in speed that you can kind of observe in say pure Python and in NumPy when working with these things. But first, let's just play a little bit with them. So I'm just going to create a few arrays. So first, let's X just be 0, 1, 2, 3, 4, just a range. I'll do Y, that one I can do explicitly, just be, say, -1, 0, 1, 0, -1. And finally, I'll do one Poisson distributed 3x3 matrix, like this. So now I have some X and Y, both of those are 5 vectors, or just length 5-element arrays. And then this A is a 3x3 matrix. With the Poisson distribution, we get integers, so it's an integer array. Now, what we can do, which may seem very intuitive, or it may seem like magic, depending on kind of your background, is that I can now just say X plus Y. So X is a 5 array, Y is a 5 array. So if I just say X plus Y, what it does is that it adds these together element-wise, which happens to be the same as you'd get, say, in mathematics if you have 2 vectors and add them together. So in this case, Y is explicitly up there. And we can see the first element of X would be 0, so 0 plus -1 becomes -1. For the second element of X is 1, so we get 1 plus 0 is 1. The next element of X is 2, 2 plus 1 is 3, and so on and so on. And similarly, we can kind of do element-wise multiplication, so x times y. And now, for instance, on the last element, we have y is -1, and the last element of x is 4, so 4 times -1 is -4. There are also different functions in NumPy. So for instance, we could do the exponential of x. And this now is the exponential, so e to the power of x. So it's done for each element. So we get e to the power 0 becomes 1. E to the power 1 is 2.71. E to the power 2 is 7.38, and so on. What happens here is that under the hood somewhere, there is some looping happening, right? Because we're getting something applied to many different elements. But this happens really down in C code, which is what NumPy is written in, which happens to be much faster than if you do loops in Python. And this is kind of one of the mantras when you're doing scientific computing, is that if you end up writing a for loop in Python, it will be slow. And that kind of comes back to what we talked about in the beginning, that Python is extremely flexible. So if you're doing a loop in Python, at every point in the loop, Python needs to check, is this thing still what it was just a second ago? So it just runs all of these checks, which are complete overhead in most cases, because things usually don't change like that, but they can, so Python needs to check. And then in NumPy, we've kind of given it the guarantee that, well, every number in this array would be a float. So you don't need to check it. So that's kind of why NumPy loops are much faster than Python loops. And the way to write NumPy loops is to not write loops at all. You just deal with these vectorized functions. These vectorized functions come both in the shape of just being operations, like your plus and minus, and it comes in the shape of being this np dot functions. So np exp here, and if we just do np, and in Jupyter, I can just hit tab to see a list, and many of these, like ups, the absolute value, are min and max stuff. Here we have all the arc, cosine, and so on. Many of these are the mathematical functions that will be vectorized. So yeah, for instance, we could do npcos like this. Just to show you that these things really are faster. So this is a special thing you can do in Jupyter or in IPython. So depending on how you're running, it may not work for you. But let's say that I just create a list of numbers, and I'm going to create a slightly larger one in this case. And I'll do the same as an array. So here I've just created two objects. One is a list of 1 million numbers. The other is an array of 1 million numbers. It's not too important exactly what this is. I just want to have something that's slightly bigger, just so that you can see the runtime of this. And then this is a cool trick in Jupyter. You can do %% time it, and it will run timings of whatever happens to be in that cell. And then if we're working with the numbers, or let's do the NumPy one first, I guess. If I want to just calculate the squares of these numbers, I can now just do numbers arrays to the power 2. And this now calculates the squares of 1 million numbers. And you could see when I run this under time it actually took a couple of seconds to run. And that's because it runs it many times. In this case, it says here it ran 1,000 loops in 7 runs, so it ran the code 7,000 times. And then it calculates how much time it spent on this. So this tells me here that, okay, it spent 628 microseconds, and it saw a little bit of variance between each of them. But in general, we're spending around 600 microseconds to calculate this. We can then do the same thing but in pure Python. And one way to do the same kind of loop in Python would be to use something called a list comprehension. So I don't know if, let's see, no. Okay. For x in numbers list. So what I'm doing here is that I explicitly need to type out the for loop. And with this comprehension, I'm kind of saying that, okay, put this back into a list. So I'm getting the same result. I'm getting the squares here. I'm just saying for every number in numbers list, calculate the square of it and put it back into a list, essentially. And in this case, you can see that now it took about 40 milliseconds. So let's see, that's close to 100 times slower. Well, let's be fair, more like 70 times slower or something in pure Python than in NumPy. And those kind of differences is something that you easily see in these calculations. Of course, when it's just microseconds, it doesn't matter, but if you have a calculation that is a little bit bigger, you could be thinking about seconds versus hours. So it's really, you really should take advantage of the vectorized operations. There's one operation that I just want to show now. It's kind of as a prelude to the linear algebra thing. And that's what's called a dot product. So we saw that if we do something like x times y, this is doing element-wise calculations. So first element times this first element, and so on. There is something that looks similar, but maybe slightly weird, is that you can use the at symbol. So x at y like this. And what this does is that it calculates the dot product between two arrays. And depending on what you're kind of giving it, it means, well, slightly different things, I guess. If you just do arrays like this, what it's really doing here is that it's doing the element-wise multiplication and then taking the sum afterwards. So you can see here -2 is the same as, if you look in the line above, 0 plus 0 plus 2 plus 0 minus 4. That ends up being -2. But if we're having matrix times vector or matrix times matrix, then this actually turns out to be the matrix multiplication. So we'll see this soon, but just as a quick example, recall that we had this A, and let's see, if I now just define a Z vector, let's do 1, 0, 2 or something. I can do something like A times Z. And this is now the matrix A times the vector Z. Essentially, what we end up with then means that we get, let's see, 5 there times 1, plus 5 there times 0, plus 4 there times 2. So that's 5 plus 0 plus 8, which is 13, so that gives us the first element there, and so on. We could also do this with matrices. So if I do something like A times A, I'll get this thing. Okay, in the next section, we're going to dive a little bit deeper into some of the linear algebra stuff. But let's just do a few minutes where you play a little bit with just vectorized code. And here it's essentially just asking you to, pick one of these functions and write it out as a vectorized function and write it out as a loop. And just have a look at the difference. See how the vectorized version actually is better, both in terms of readability, once you kind of get used to them, and as we've seen also in terms of performance. So yeah, so let's do a couple of minutes for this one. Okay. Any questions about vectorization? So we'll move on and talk a little bit about linear algebra capabilities of NumPy. But just a note, so if there's kind of one takeaway from this tutorial, it is use vectorized operations. It's kind of the whole mantra of NumPy. Okay, so linear algebra is all about matrices and things like this. And you've already seen that we can do some other things like matrix multiplication and so on directly in NumPy. There's also a np-linalg module that kind of comes with some other linear algebra features. Let's see. So you can kind of do, let's see, where are they? Really down to typical matrix stuff if you're really working with those, like Cholesky, QR stuff, eigenvalues, and so on. We'll look a little bit at these more common ones, and then there are also things like the dot product and so on that we've already seen in plain NumPy. So one of the things that you want to know, or when you're dealing directly with matrices, is think about the determinant. We're not going to cover the math of this now, so if you don't know what the determinant is, don't worry too much about it. But this is kind of just essentially calculating the size of a matrix. So it gives you this thing. Another way to figure out the size of a matrix is to look at the norm. That's also directly in there. It's in many cases possible to calculate the inverse of a matrix. And the inverse of a matrix is essentially what you need to multiply a matrix with to get back the identity matrix. So here it's kind of just some random numbers that we're seeing. But we can see that if I calculate this new matrix and multiply it, as in matrix multiply it with A, I'm still just getting some weird numbers back. But if we look closely at this now, we can see on the diagonal there are ones, and the numbers that are off the diagonal are all very small. So you see this E negative 16 or 15 there. It essentially means it's very close to 0. And if we had been able to calculate things completely precisely, it would have been 0. So it kind of gives us back the identity matrix. So this is similar to the inverse of a number is 1 divided by that number. So 1/2 times 2 equals 1. Another operation that you may want to play with is just a transpose. So let's see. So the transpose is just essentially the symmetrical twist of the regular matrix. So you can see these two matrices, if you do, they're just kind of mirrored along the diagonal. Okay. In practice, though, for many applications, you don't really work with these square matrices where these things are well defined. That's more theoretical math usually. Often you have, say, if you're doing more like data science stuff, you want to calculate some least squares approximations of things. So you'll have, for instance, many observations and try to fit a line through them or some model to that line. So the least squares approximations are also handled inside of here. So just to show a quick example of this, let's redefine now a new array that is not a square matrix. So I'll just do a fairly simple one. Like this. And then let's see, did we miss that one? So if we're just looking at this, we can see this is a 3x2 matrix. It has 3 rows. And one way to think of this is that it's defining a system of equations. So if I have 2 unknowns, say x and y, I can think of this as being 1 times x plus 2 times y equals some number, and 3 times x plus 0 times y, and 0 times x plus 2 times y. So it gives me 3 equations. And then on the right-hand side, I can then have the numbers from b that you see up there, 30, 15, and 20. That means I have x plus 2y equals 30. There's one representation here. If we're just solving this manually, you can see that 3x equals 15 means that x is 5, and 2y equals 20 means that y is 10. But that's not compatible with x plus 2y equals 30, because that would be 25 instead. So if we're just looking at it like this equation doesn't have any solution. However, we can find a best solution, which is what we always do when we're kind of doing modeling. One of the basic ways to do this is just to do what's called the least square solution, which kind of gives us the least error of this. So this we can do either very manually by doing finding the inverse of A. This will now show me an error, mainly because the mathematical inverse of a matrix is just defined for square matrices. But there's something called a pseudo-inverse, which is kind of almost like an inverse, and it's something that's possible to calculate for weird matrices as well. And it kind of has the feature that if I multiply this by A, I'm getting back something that is an identity for both ways. But you can see it has this the same, or I guess the twisted shape of A. And it actually gives us the best approximation in the sense that if I multiply this by B, I'm getting the best approximation of B to our system in the least square sense. So doing this is now our least square solution. And you can see it's close to 5 and 10, but it's kind of dragged off a little bit by the first equation. Or we could also, instead of kind of diving into the math of this, there is a least squares function. That throws a warning at me. I'll do what it tells me, which is essentially specify that arcond is none. But what we can see here is that it has also, let's see, it has the same least square solution as the first return parameter there. It also gives us a little bit extra information about, let's see, we can just ask it. One of them is kind of saying, let's see, returns. It returns the best array, it returns the residuals. So how bad is this solution? It returns the rank of a matrix and the singular values. So this thing there is the same as that thing over there. Okay. Any questions about the linear algebra part of this? Let's see. Then let's do a few minutes just with playing a little bit with these things yourself. So we can calculate matrix, play with the different transpose determinant, stuff like this, or jump directly into the least squares if you just want to get your hands dirty on those. Okay, are there any questions that came up? No, so for the last part of the tutorial, I want to talk about something called broadcasting. And this is kind of cousin to the vectorized operations, and it's kind of the other superpower of NumPy, and something that makes NumPy code both, well, in particular, look very readable, but also it helps a little bit with performance. So what is broadcasting? Let's see. So yeah, let's go back to now let's just use this one. So I have an array like this, 3 by 2 array, and let's say that I also have a 2 by 3. Yeah. I have a vector that I messed up somehow. Shouldn't be array. And I also have a vector like this. So we've seen that we can just do vectorized. Yeah, exactly. That we can do vectorized operations in NumPy. So I can just say something like a plus x, and it will calculate stuff together for us. I said that this is done element-wise, so it kind of matches the elements. And that is true, but it actually does this even more powerfully using something called broadcasting. So in this case, you can see that I have the A array, which is a 3 rows by 2 columns matrix. And then I have the X, which is just an array with 2 elements. And still it's able to do A plus X together there. And what it's doing is that it's just matching really from the end, so the last dimensions. So the 2 columns are matched to the 2 elements in the vector. And then the other dimension, it's kind of broadcast over it, is kind of what we're saying. So the end result of this is that if you look at the A plus X there, you can see that it becomes 1, 2 in the first row becomes 3, 6. So it does 1 plus 2 from X, and then 2 plus 4 to get the 3, 6. But then it does the same thing on each row. So the 2, 4 is kind of applied on each row. So this ends up being the same as if X had been a 3 by 2 matrix that was 2, 4, 2, 4, 2, 4. There was a question. Let's see if I can find this one.
A column, because then...
Okay, yeah. Let's see. So yeah, so the question is essentially, can we do this by column instead? So the rules for broadcasting is that it starts with the last dimension, which happens to be the column. So in that sense, the answer is no. It kind of needs to start from there, but that's not completely true. Let's have a look at if I have y then, and I now want to apply this to the columns. If I do a plus y, it will yell at me and say that I can't do this. And you can see there it says the broadcast word, and it shows us the shapes we had with 3, 2 and 3, comma. And what we need to do is kind of match the dimensions from the end, so the 3 is matched with the 2. But one thing we can do is that we can change a little bit with the dimensions of y. So if you remember from the very early, I show that we can do something like this, where I create a new axis. And what this thing does is that it has the shape 3, 1. So that means that if I want to match this one with the 3, 2, I'll start at the end, and it says, okay, I have something that's 1 element versus 2 elements. And as long as one of those is just one element, it's okay. Then it can explode that out. And then we can see the 3 and 3 matches. So that means that I can actually do a plus y, but where I create this new artificial axis for it. And you can see if we look at, let's see, did that one? I guess I want to show this one. So this one-dimensional 2, 4, 6 array there is then first converted into this 2-dimensional thing that matches what I'm doing. And now I can do the broadcasting along columns instead. So it's a little bit more cryptical, but it can still work. And we can now see that, let's see, what did we have here? We had 1, 2. Both of those are added with 2. And then the 3, 0, I add 4 to those. And this was 0, 2, I add 6 to those. Okay. One thing where we use this broadcasting a lot is that it simplifies how to deal with scalars, so just numbers. So far we've seen that I could do, let's see, what did I do? Something like a plus x, where both of these are NumPy arrays. But I can also just do a plus 5. And now I've added 5 to every element there. So the number 5 is treated as a NumPy array with just one dimension in each, or one element in each dimension, and then it's kind of just exploded out so that it's really, every element is then added to 5, or I could do 3 times a like this, or we could just continue in this manner. So that's one of the really common use cases for broadcasting, is just doing with the scalars. So yeah, when you can broadcast, the rules are really just that you just compare dimensions, and as long as they're either the same or one of them is 1, then you can broadcast. And this gives you a lot of cool things you can do, like even if you have a list of, say, matrix multiplications you need to do, you can do them vectorized by just jamming everything into a higher dimensional matrix and so on. So in the final exercise, and I see we have like 3 minutes to do this, there are some kind of showing a little bit of how you can do this. I see that, yeah, we probably don't really have time to go through these, but feel free to play with these yourselves. And as I said, you can find solutions for all of them. But I think we'll kind of, for the last 2 minutes, just check if there are any questions, comments, anything you want to end with. Feel free to seek me out during the conference if you have any other questions, or just send me an email or get in touch otherwise. Then I'll also note that in the next tutorial in this room will be about pandas. And pandas is a tool for different kind of data science, and it's partly at least built on top of NumPy. That's kind of about to change a little bit. But when you're working with pandas, you're typically really doing NumPy under the hood. So everything you've kind of seen here, to some extent at least, holds through also when you're doing pandas. And similarly, with many of the other scientific Python packages like scikit-learn and so on. So yeah, so this is kind of what's underpinning almost everything that's done in scientific Python. Have fun with it.